All right, welcome back, everyone. If you've ever just casually flipped a light switch, plugged in your phone, or wondered exactly how your electric heater knows just how hot to get, well, you have personally interacted with one of the absolute fundamental principles in all of physics. Today in this explainer, we are decoding Ohm's law and circuit resistors. I want you to think of an electrical circuit as a busy, high-speed highway system. Just like any highway, there are engines driving the cars, there's the traffic itself, and of course there are speed bumps and roadblocks along the way. So let's figure out exactly how to navigate this microscopic road together.
Okay, let's dive into this. Here's our roadmap for today. 1. Understanding Ohm's law. 2. The role of resistance. 3. Series versus parallel circuits. 4. Everyday circuit applications. And 5. Test your knowledge. Section 1. Understanding Ohm's law.
So to really grasp Ohm's law, you kind of need to understand the three main characters in our circuit story. First up, we have voltage, represented by V. Think of voltage as the push or the engine power. It is literally the pressure forcing everything forward. Next is current, represented by I. This is the flowing traffic of electrons themselves, just zooming down the wire. And finally, we have resistance, represented by R. These are the speed bumps, the narrowed lanes, the elements actively opposing the flow of that traffic. Ohm's law is the fundamental relationship that defines exactly how these three forces interact with one another.
And this whole relationship, it's beautifully captured in one simple, incredibly famous formula. V equals I times R. Voltage equals current multiplied by resistance. So the crucial takeaway here is that they are mathematically locked together. If you increase the voltage, like if you push harder, and you keep the resistance the same, the current absolutely has to increase. More push equals more flowing traffic. But if you increase the resistance, say you add more speed bumps, while keeping that voltage the same, the current is inevitably going to drop.
Section 2. The role of resistance. So what are these speed bumps exactly? Well, electrical resistance is officially defined as the opposition to the flow of current. It's measured in ohms, which is that standard SI unit you're going to see in all your physics problems. And if we just do a little algebra and rearrange our Ohm's law formula from a minute ago, we calculate it as R equals V divided by I. Ultimately, resistance is essentially how much voltage it takes to push a very specific amount of current through the wire. Now, what's really interesting about this is what physically causes that resistance in the real world. It basically comes down to four varying road conditions. First is length. Simply put, a longer wire means a longer journey for the electrons, which naturally means more resistance. Next is cross-sectional area. Think of this as the number of lanes on our highway. A wider wire has more area, allowing more electrons to flow freely, which actually lowers the resistance. Third is the material itself, known as its resistivity. Copper, for example, is like a smooth, freshly paved road, while other materials are more like driving on chunky gravel. Finally, temperature. Heating up a wire generally increases resistance because the atoms inside start vibrating more, which makes it a whole lot harder for the electrons to pass through seamlessly. And we can actually wrap all those physical factors up into one neat little mathematical package. R equals rho times L divided by A. Resistance equals the material's resistivity multiplied by the length of the wire divided by its cross-sectional area. The takeaway here is super intuitive. If you want to increase resistance, you make the wire longer or thinner. If you want to decrease it, make the wire shorter or thicker. Now, in real practical circuits, engineers don't just rely on random wire properties. They actually manufacture specific components called resistors to purposefully control this electrical traffic. And you've got a whole lineup of them. There are fixed resistors, which always provide the exact same unchanging amount of resistance. You have variable resistors, potentiometers, and rheostats, which let you manually adjust the resistance, kind of like twisting the volume knob on your car stereo. Then you have the smart resistors, things like thermistors, which automatically change their resistance based on temperature, and LDRs, or light-dependent resistors, which change entirely based on how much light is hitting them.
Section 3. Series versus parallel circuits.
All right, so what happens when we start wiring multiple speed bumps together? Let's look at the first method, a series combination. In a series circuit, components are connected end to end, forming one single continuous path for the electrons to flow. Because there's literally only one road, the traffic, the current, stays exactly the same everywhere. But the voltage, the push, gets distributed and used up across each and every resistor. Calculating the total resistance here is incredibly easy. R total simply equals R1 plus R2 plus R3, and so on. You literally just add the speed bumps together. But let's see how this builds when we completely change the road layout with a parallel combination. In parallel, the circuit actually branches out into multiple separate paths. And here, the rules totally flip. The voltage is actually equal across every single branch, meaning every path gets the same full push from the battery. But the current divides up, choosing different paths to travel down. Now, because we're essentially adding more lanes to our highway, adding resistors in parallel actually reduces the total equivalent resistance. The math is a bit different for this one. 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Comparing these two directly, the core differences are crystal clear. On one hand, you have the series circuit, a single path where the current is constant but the voltage distributes. The big downside here, if just one component breaks, the whole road is completely blocked and the entire circuit stops working. On the other hand, you have the parallel circuit, multiple paths where current divides, but voltage remains totally equal everywhere. The huge advantage here is that if one path breaks, the electrons can just detour and still travel down the other branches. Section 4. Everyday circuit applications. Now, we aren't just doing physics theory here. These concepts, Ohm's law, resistance, series and parallel circuits, are literally the governing rules for everything you use on a daily basis. Your household wiring? It's all done in parallel. That is exactly why you can turn off the kitchen light without accidentally shutting off the refrigerator. Electric heaters and irons use specific high-resistance wire that deliberately gets incredibly hot when current tries to push through it. Your mobile chargers use highly precise resistors to ensure your expensive phone battery gets exactly the right voltage and current it needs to charge up safely without, exploding. Mastering these formulas literally means mastering the modern world. Section 5. Test your knowledge. All right, it's time for a quick active recall quiz to really lock these concepts in. Question 1. Imagine you're looking at a circuit. If the resistance increases while the voltage stays exactly the same, what happens to the current? Take a second. Got it? The answer is the current decreases. Remember our golden rule? Ohm's law, V equals IR. If the push of the voltage stays flat, but you suddenly add a bunch more speed bumps of resistance, the flow of traffic has absolutely no choice but to slow down. Okay, moving right along. Question 2. Think back to our road layouts. Which type of circuit connection provides multiple paths for the current to flow through? And the answer is a parallel connection. Just like a highway branching off into all sorts of different exits and side streets, parallel circuits allow the electron traffic to divide and conquer. All right, last question, and this one is really going to test your memory on the math. We know the general parallel formula involves fractions, but for exactly two resistors in parallel, what is the handy shortcut formula for calculating their equivalent resistance? Let's see if you remembered. The answer is R equals R1 multiplied by R2, all divided by R1 plus R2. This is also known as the product over sum rule. If you got that, you are in incredibly great shape for calculating circuits quickly. And just like that, that wraps up our journey down the electrical highway for this explainer. We've decoded Ohm's law, we've uncovered the true nature of resistance, and we've successfully mapped out both series and parallel routes. The next time you plug in your phone, you'll know exactly how the current navigates the road. But I want to leave you with this thought. If we didn't have these electrical speed bumps to perfectly control the traffic, would a single piece of our modern technology even exist? Something to think about. Thanks so much for joining me. Keep asking great questions, and I will see you next time.